Good morning. Welcome to my presentation called Holographic Measurement of the 3D Sound Field using Nearfield Scanning. My name is Dave Logan, and I will be presenting some of the details regarding the research and development performed by Wolfgang Klippel, Christian Bellman, and Daniel Knobloch in developing the Nearfield scanner. I plan to tell a compelling story, starting from the limitations of our current measurement techniques and ending with some test cases that prove these limitations can be overcome by using this new technology. We will cover pros and cons of conventional loudspeaker measurements, new requirements for comprehensive 3D directivity data, introduction to directivity measurements, near-field measurements can be beneficial, a new and better way using near-field scanning, what is spherical harmonic wave expansion? We'll talk about coefficients, spatial resolution, number of measurement points, and the order of the expansion. I'll provide some practical applications and some test cases, and then I'll conclude with some conclusions. Let's begin with a history regarding current measurement techniques. In the early 30s, Beranek and Sleeper developed the anechoic chamber. It's absorption of room reflections above the cutoff frequency. It has high ambient noise isolation, and it has controlled climate conditions. Later, in the late 60s, early 70s, Heiser, Berman, and Fincham developed the gating of the impulse response, which was suppression of room reflections at higher frequencies. It had higher signal-to-noise ratio due to ambient noise separation, and limited low-frequency resolution, and it depended on the difference between the direct sound and the first reflection. Our current measurement techniques are not perfect, and they suffer from the following problems: low frequency accuracy and resolution limited by the acoustical environment, which is the room dimensions and the acoustic treatment. Far field measurement conditions are required. Accuracy of phase response depends on the temperature deviations and movement. An anechoic chamber is not perfect. Dimensions and irregular absorption are the limitations. An anechoic room is an expensive long-term investment which cannot be moved easily. One major limitation is the dimensions of the acoustical environment. Room dimensions are the limiting factor for low-frequency measurement accuracy and resolution. Why do we need to make measurements in the far field? Because what is heard and measured in the near field is difficult to predict and not a reliable indicator of events in the far field. In the far field, the source is small compared to the measured distance, and the sound level falls at 6 dB per doubling the distance. This is the inverse square law. The inverse square law does not apply in the near field. As a consequence, sound pressure measured in the near field cannot be extrapolated into the far field. Problem number 3, phase response accuracy. Sound velocity is dependent on air temperature. Temperature difference of 2 degrees Celsius means a change in velocity of 1.2 meters per second. At 5 meters, this relates to a delta in time of 0.1 milliseconds. And this leads to phase errors at higher frequencies where the wavelength is small. In general, far field measurements are prone to phase errors. Problem number 4, no anechoic room is perfect. How to cope with limited absorption at low frequencies. We select a reference loudspeaker sample. We measure in the far field in an anechoic room. We measure again under free field conditions. And then we calculate a room correction curve and apply it to a simulated free field response. However, new requirements for a changing industry. There has been a recent increase in demand for 3D directivity measurements. In home audio, to predict how a loudspeaker might sound in a typical listening room, CEA 2034 last year specifies a 360-degree polar measurement largely based on the techniques developed by Toole and Devanchier at Harman, aka we call it the spinorama test. Today's handheld personal audio devices, the near-field response generated by laptops, tablets, smartphones, etc., is more important than the far-field response. This will be considered in the new IEC proposal 60268. Studio monitor loudspeakers. Professional reference loudspeakers need a careful evaluation in the near field. And professional stage and PA equipment. Accurate complex directivity data in the far field is required for room simulations and sound system installations, mainly line arrays. So how do we make directivity measurements in the far field? The sound pressure is measured at multiple measurement points located on a surface of a sphere with radius r. The DUT is rotated. The number of points depends on the desired resolution. In a lot of cases, this is not practical. We need too many measurement points for fine resolution. The accuracy of the measurement depends on the tolerance of mic placement, both in theta and r. We need to maintain the acoustic center when changing the DUT position. Sound reflections from the turntable. Room absorption or irregularities. And temperature deviations and air movement. When we want to reduce the number of measurement points, a weighted spatial averaging can be used, but it is an estimation. Near-field measurements can be beneficial. The advantages of near-field measurements are a high signal-noise ratio, typically 20 dB more than the far field. Amplitude of direct sound much greater than room reflections, giving good simulated free field conditions. Minimal influence from air properties, air convection, temperature deviations. Faster measurements since no averaging is required. Measurements can tolerate some ambient noise from the office or the workshop. Disadvantages: it's not a plane wave. The sound velocity and the sound pressure are out of phase. And the inverse square law does not apply. Therefore, you cannot extrapolate the sound pressure into the far field. This is the main limiting factor, the inverse square law. However, there's been some recent contributions, scanning sound and the sound field on a surface around a source. These were introduced by Weinrich in 1980, Mellon, Legreen, Garcia 2009, and Mr. Bai in 2012. So there's a new and better way where we exploit the advantages of near field measurements and overcome the disadvantages using spherical harmonic wave expansion. This is what we get. We get near field sound pressure can be extrapolated into the far field now. It's no longer a problem. Room dimensions are no longer a factor. No anechoic environment required. Far field conditions are no longer necessary. High spatial resolution can be attained using less measurement points. Comprehensive data set. One measurement does all. The 3D acoustic output is the result of post-processing. Faster 3D directivity measurements. Here's how we do it. The general approach. Step 1, we measure in the near field sound pressure using robotics. Step 2, we do a spherical harmonic wave expansion. Post-processing of the measured near field data includes sound field separation techniques. Step 3, extrapolation. Calculation of the sound pressure at any point outside the scanning surface, both in the near field and the far field. Step 1, the scanning process in the near field. The question is, do we move the DUT or the mic in the near field? The advantages of moving the mic are as follows. You get accurate positioning. You can facilitate heavier loudspeakers. You have constant DUT interaction in the room during the scan. This is important when we're doing measurements in a non-anechoic environment. We require minimum gear within the scanning surface. Only a platform and a pole. No rigging materials to support the heavy loads. We can go one step further. We can say, can we scan multiple layers and to facilitate a field separation? The double layer scan provides information about the incoming and outgoing waves, which can be used to separate the direct sound from the room reflections. Under anechoic conditions, The high signal noise ratio in the near field combined with wave expansion techniques eliminates the need for field separation. In other words, we need to use field separation in a non-anechoic environment. The spherical wave harmonic expansion, step 2, this is how it's done. In the near field, we get our scanning data. And then we use a set of basic functions. They're general solutions of the wave equation. These are the harmonics, the spherical harmonics. From this, we will receive a matrix of coefficients which describes the loudspeaker characteristics. From there, we can get the results on the scanning surface, and we extrapolate into the far field reconstructing the transfer function. How do we interpret the coefficients? The coefficients are complex and frequency dependent. They weight each basic function of the solution of the wave equation. The number of coefficients depends on the frequency and complexity. A direct relationship between the complexity of the sound field and the number of coefficients is required, which in turn relates to a number of measurement points required. As the frequency and/or the complexity of the sound field increases, the order of expansion will need to increase accordingly. This will avoid aliasing. Unique properties of this process: it has significant data reduction occurs when the measurement points are converted into coefficients. Truncation of the order has the effect of smoothing the directional properties, the lobes in the sound field. And wave expansion interpolates between the measured points. This is how we can reduce the number of measurement points when we convert down to coefficients. How many points do we need to measure? The number of measurement points depends on the loudspeaker type. In other words, the complexity of the sound field. The symmetry of the loudspeaker is also a factor. Application demands a high resolution ease data. Field separation, is it required? Are you in a non-anechoic environment? In general, the number of points is 1.5 times the number of coefficients. That's just in general. We are capable of making a 1-point measurement using a reference measurement setup. I'll explain that later. Sound power directivity takes approximately 80 points, less if you're in an anechoic environment. Normal scan can take between 200 to 500 points. High-res scan, 2,000 points. The number of measurement points required is much lower than the final angular resolution of the calculated directivity pattern. This is important. High angular resolution only requires a few measurement points. Example, a woofer at low frequencies. The sound field has limited complexity and can be characterized by a small number of basic functions. For instance, a directivity pattern at 200 hertz is the target. We measure 1 point, we get 1 order, and we can almost reproduce the target. As we measure another order, we get closer to the target. As we progress from a dipole to a quadrupole, spherical harmonic, our orders increase to 2. We're getting better and better. By the 3rd order, we have it completely replicated. N equals 10 is redundant. We don't get much gain. So you can see that the sound field is completely described by an order of 3, which requires 16 coefficients, which is approximately 25 points. How do we check the accuracy of the wave expansion? Well, we look at the fitting error. The number of measurement points is larger than the number of coefficients, which leads to a fitting problem. a redundancy of information. This redundancy is used to calculate the fitting error in dB. For example, at 100 Hertz, we have a fitting error of minus 35 dB. This is calculated based on the fact that 100 Hertz, n equals 0, almost completely describes the sound power. And the remaining coefficients have a smaller influence. Therefore, they are redundant. However, at 1 kilohertz, an order of 3, which is not sufficient to completely represent the sound power, and the fitting error increases accordingly. The fitting error indicates potential problems, poor signal-to-noise ratio, insufficient order, geometrical errors in the scanning. We have bad signal-to-noise ratio below here. The speaker's not producing anything here. And at higher frequency, we need more order, higher than order 3 here. How do we find the maximum order? The measurement system determines automatically. Optimum order n of the wave expansion, total number of the measurement points, and the measurement time. We have a target, directivity at 2 kilohertz. Our level at 1% fitting error. And our order of 0. You can see that the fitting error is out of the acceptable, above the acceptable tolerance level of 1%. As we increase the order, the fitting error starts to get better and improve. As we keep increasing, it gets better. And then we reach an order of 10, and you'll see that most of the fitting error is below the 1% level, except for some signal-to-noise ratio in the low frequencies, which the speaker's not producing. So we get a good match, sufficient accuracy with n equals 10. Test case number 1. SPL comparison of an anechoic environment versus a reverberant room using a line array. The main thing here is the difference, the only difference is the number of points that were measured in the far field in an anechoic chamber was 16,200. Compared to a 4,000 point near field scan in a reverberant room, which is the worst case conditions. Here's the measured sound. And this is the direct sound, which we measured, or not measured, but it's actually calculated from subtracting the room reflections. So you have the measured sound minus the room reflections gives us the direct sound. Field separation is required because we are in a reverberant room. However, above a certain reflection frequency, we can use the time windowing and gated impulse response. The benefits of field separation: no anechoic conditions are required. There's no time windowing. High resolution. Low order of expansion. Minimum number of measurement points, less than 20. So even though we measured 4,000 points, we only needed 20 at low frequencies to use field separation. Better accuracy using near field scanning. We're comparing the far field measurement in green in an anechoic room to a near field scan in a reverberant room. We can see problems at the frequency limit of the anechoic chamber. And we also have some symmetry in the high frequency area. There's some symmetry in the anechoic field and far field measurement, which is causing us a small error there. You can see it in this polar plot. The red curve is its symmetry is not very good. So near field scanning and field separation can remove room modes in the reverberant environment. More angular resolution with less points. This slide demonstrates how a 4,000 point near field scan has an angular resolution that is comparable to a 16,200 point conventional measurement in the far field. Wave expansion interpolates between the measurement points. Case 2, directivity and sound power using a studio monitor. This slide shows the directivity versus frequency in both the vertical and horizontal planes. The goal is to achieve controlled directivity in the near field. In the vertical, we have a separation between the woofer and the tweeter and a contour plot. And in the horizontal, we have a more controlled directivity. So we can use this data to improve the sound field in the near field. What is the accuracy of a sound power measurement? It only takes 20 minutes to perform it. This is the curve of the radiated sound power, 2,500 points. It took 8 hours to do it. We repeated at 100 points, took 20 minutes. Below 10 kilohertz, there's only a deviation of half a dB. Above 10 kilohertz, it's less than 1 dB. Fitting error from the post-processing shows the accuracy of the results. Here's the fitting error at 2,500 points. There's the 1% threshold. There's the fitting error at 100 points. It's fairly close. Noise in the low frequencies, and we need more higher order to measure the more complexity above 10 kilohertz. We satisfy the requirements of CEA 2034. We can reproduce this requirement using this tool. Fast single-point SPL measurements in the near field are possible using a correction curve. The assumption is loudspeakers of the same type with similar geometry have similar directivities. We do a single-point measurement in a non-anechoic environment. We see room reflections. See errors in the near field. 1 point is insufficient for the correct processing. We can't do field separation because of that. There's no far field extrapolation possible. So what we need to do is we need to do a complete scan of the reference DUT. And from there, we can calculate the room correction curve. We can apply it to the 1 point measurement, and we'll get the near field response with the room reflections removed. Then another correction curve for the extrapolation, and we apply that as well. And we get the correct curve in the extrapolated far field. This method allows a single point on-axis measurement for transducer and/or crossover development comparisons. In other words, a full scan is required initially, but after that, a single point measurement will be sufficient. Test case number 3. Comprehensive 3D information using a laptop. Is the user located in the near field or the far field? This is a curve of the apparent sound power versus distance, and we have our order plotted from monopoles and increasing. In the near field, the sound power is not constant. In the far field, the sound power is independent of distance and is therefore constant because the sound pressure and velocity are in phase. So you get no losses from the imaginary reactive component. We can use this to determine where the user is in the sound field. Determine location in the near and far field is important for personal and handheld audio devices. Comprehensive 3D information supports the evaluation of spatial sound effects. Again, the laptop, and we have listening points. We can have listening points simulating the left and right earlobes. We get a different curve at each position in the near field. You know, and it's windowed within a observatory plane. And we get the comprehensive information. We get amplitude, SPL distribution at 3 kilohertz, and we also get phase. We can actually see the phase changing at 3 kilohertz. Near field information is important for 3D sound effects. We have a listener in the near field. We also have a listener in the far field. We can produce curves for both. Notice that in the far field, the variation of SPL changes with distance. And we can get comprehensive information from this as well. Sound pressure distribution at 3 kilohertz on an observatory plane. Listener in the near field and a listener at 3 kilohertz in the near field with the phase information. Summarize a new and better way. Holographic measurement of the 3D sound field using near field scanning provides the following benefits. More information about the acoustic output, both the near field and the far field. Sound pressure at any point outside the scanning surface, complete 3D space. Improved accuracy compared to conventional far field measurements, coping with room problems, gear reflections, positioning, air temperature. High angular resolution with less measurement points. Simplified handling, no moving of heavy loudspeakers. Dispenses with an anechoic room. Self-checking by evaluation of the fitting error. Comprehensive data set with low redundancy. Thank you. Is there any questions? Yes.
I'll pick it off with one. We deal with very strangely shaped products. Think of like the Zeppelin speakers. Does that mean that your radius has to change on what you're scanning through?
The dot geometry, it's all covered inside a cylinder that's scanned. So you have your entire dot. It sits inside a cylinder that you're going to scan around it, an imaginary cylinder. The total diameter of that dot will determine how big the cylinder will be in diameter, and the total height of the dot will determine how high the cylinder will be. If you have drivers that are several drivers, or if they're mounted in a strange configuration, then the complexity of that sound field will increase. And if you have a higher complexity of sound field, you're going to need more coefficients and a higher order and more measurement points to measure it. But as long as you can get the entire dot inside a cylinder, and we can scan the cylinder, it doesn't matter about the geometry.
Is there any consequences of the diameter of your scanning surface?
The only limiting factor is the machine itself, how wide a diameter it will measure in the radius and the height. Right now, I think our limitation is about 2 meters by 2 meters. However, it could be developed into anything really. Yes?
Have you done a complete measurement of complete speakers, low standing speaker with 3-way, 4-way, whatever, meter high, something like that? Have you scanned a speaker like that?
Yes, we can do that as well. What we do is we perform, for instance, if you have a speaker that's higher than a meter, then you would scan it possibly 3 times. I have a slide that actually shows that. If you give me a second, I'll look it up. So this is how we measure tall speakers and sound bars. So we have a very tall speaker. What we'll do is we'll measure it 3 different times. Once in the smaller area at the bottom, the 1.5 meter area, then we'll do it again. Sorry. We'll do it again in the middle, and then we'll do it again at the top. And by picking a calibration point between the 3 scans, we can combine the information and get the same results.
What is the maximum height of the one scan?
Right now, with the current setup, this slide shows 1.5 meters. Yeah. Anybody else? Yes?
Yeah, what I don't understand is how you do this decomposition, because you measure it from the cylinder,
Yep.
from the device, you measure different points, scalar, sound pressure.
Yep.
And if you measure just at one point, you can make an estimate of what that meant when you're saying if that was a monopole, it would be such and such.
Right.
If it was, how do you go from there then to the next harmonic, to the dipole? Do you need to take 2 measurements?
No, if on the cylinder surface, we need so many orders in the expansion. So the order of the expansion determines how many coefficients we need to represent the loudspeaker, and then the number of coefficients also relates to how many measurement points we need. So in the actual expansion itself, if we require 10 orders to reproduce at a certain complexity, then we will need 10 plus 1 squared coefficients, which is 121 coefficients. And if we need 121 coefficients, then we need approximately 200 points. So it's all in the expansion mathematics. Yes? Yes. Yeah, we need both. Yes. Yeah, we need to measure the cylinder, and then we need to, because we're in the near field, we need to do the spherical harmonic expansion. I'm sorry, I can't hear you. Can you repeat that?
Sorry, how does your approximation compare to some of the Hellas expansions, like the Michigan Tech guys, John Logan, and showing what you did a very significant reduction in number of data points? How does your compare to theirs? Done something like that?
I'm not familiar with their work, but we can discuss it later if you like. Anybody else? Yes?
In test case number 2, maybe I didn't get this properly.
Yeah.
In test case number 2, you were showing 2,500 points versus 100 points.
Yes.
Were they both using the same methodology? One was 8 hours, one was, 20 minutes or something?
Yes.
Were they both using the same methodology?
Same method. Yeah, same near field scanning method. We did one scan, I think it was 2,500 points for 8 hours. Yeah. And then we did another scan with
100 points for 20 minutes.
20 minutes.
So my question there was with the 100 points, you're showing very low fitting error.
Yes.
I don't understand how that makes sense. When you have so many more data points, why was the fitting error higher? This wasn't the sort of low mid-frequency range that you were showing. The green curve went way up.
Yeah, we can get the same fitting error at low frequencies.
Better fitting, or much lower fitting error for fewer points, which didn't seem intuitive.
They're roughly this. It's roughly the same. It's I didn't do any smoothing or anything on the curve, so there might be some areas that might be. But for the most part, using this technology, I can get the same results below 100 hertz using field separation by measuring 20 minutes worth of data compared to 8 hours. So that's crucial in this, and that's the advantage of this. So we can measure low frequencies at very limited number of points. Yes.
What is the process of setting up and calibrating the systems?
Yeah.
From point one to point N,
There's a,
an accurate result.
yeah, the only calibration that we need to do is well, there's two. There's a reference calibration, so we want to put the microphone on a 0 reference somewhere. Usually it's right in the middle of the cylinder. So we'll set that up. We'll tell the machine where 0 is. You know,
What decides what 0 is?
it's right in the middle, usually right in the middle of the cylinder. You can have it wherever you like. It's totally up to you during the measurement. I like to put it right in the middle of the cylinder at the bottom of the speaker. And then everything else from there works relatively from 0.
But you can move it up and down based on preference and what you think is how the speaker's going to be used.
Yeah, absolutely. You can move it anywhere you want. Yeah, yeah. And the other thing too is you have to calibrate the microphone, of course. Yes.
With the user ranging calculation, is there a requirement for the data fidelity and sampling rate, things like that? You're looking for a certain amount of points that you need in order to do the user ranging.
Yes. I don't understand the question. Can you-
So I was just looking for like the amount of information needed in order to do the user ranging based on the coefficient order.
The general rule is that the order of the expansion determines how you're going to represent your complex sound field. And if it's highly complex, you'll need more order. If it's not much complex, you'll need less order. The order, in turn, relates to the number of coefficients you need in your vector, in your matrix vector, to accurately reproduce that sound field. And then the measurement points is related to how many coefficients you need for that order. It's a very step-by-step, iterative process. Yes?
I'm just trying to get my head around how the field separation works exactly.
Yeah.
So you measure two cylinders, one close and the other.
Yep.
Is there any requirement for these cylinders to be close fitting, or can you actually use a cylinder which the output really much larger than the other one?
We usually set the distance between the cylinders based on the wavelength of the highest frequency you want to measure. Anybody else?
You showed the fitting error on axis. So what happens off axis with fitting error? Does it vary by angle?
The fitting error is not necessarily on axis. The fitting error is the redundancy of the order. So if we can reproduce an order, if we can reproduce a sound field with a small order, let's say 3, right? And I can accurately reproduce it with an order of 3, then anything else above that is redundant. And that redundancy is what we use to calculate the fitting error. And it's not necessarily on axis. It's all.
When you showed the fitting error curve, that wasn't on the axis, that was across.
That was for the entire scan.
Oh.
Yeah, no, that wasn't on axis. Sorry about that. Yep. Anybody else? Okay.
So does that mean that the fitting error is average value across the entire cylindrical space?
It's not like really an average value. I'm not so much aware of the actual mathematics behind the process, but it's the redundancy of order that you don't need to represent the sound field. And we use that to determine how well the fit is. So If you have not enough points, if you don't have enough order to reproduce the sound field, then the fitting error will be very bad. Maybe Wolfgang can help us.
Only a precise response to your question is just the error squared over all measurement points. Right. That's it. That means we have a predicted sound pressure, we have a measured one, he calculates the difference, squared and added over all points, and divides it by the total number of points.
There may be multiple large certain areas.
Of course, it depends now on the sound pressure. If you have one axis more sound pressure than on the rear side, it will contribute more to the total error. But if you have
Perfectly omnidirectional loudspeaker, then the fitting error be the same at all points.
more.
So it's not an average, it really doesn't really matter.
For us, it's, as Dave said, only a very, very nice tool to say this scan is valuable, accurate, and reliable, because we need, for other reasons, also a little bit of redundancy. It's not much, 30%, 50%. And then we get this information, and we know there are no more measurement points required. That's, by the way, the basis for the automatic finding of the measurement point numbers, which we need as a total order of the expression.
Okay, we're starting to run out of time here, so any last questions? Okay, thank you, Dave.
Thank you.